What does it signify when a comet appears to breathe? 3. Atlas, a voyager from a distant star system, is expelling 40 kilograms of water every second into the frigid expanse, far removed from the sun for such a display. Astronomers murmur, it's behaving as if alive. Yet this comet's narrative doesn't conclude there. Peculiar nickel devoid of iron, cyanide within its tail, and whispers of origins predating our own system by billions of years. Meanwhile, away from this celestial visitor, citizen scientists uncover the most extensive peculiar radio circles yet documented. Mercury and a series of celestial events align with remarkable coincidence in the October firmament, sparking speculation about a potential connection to 3E Atlas, and Blue Origin's October mission only amplifies these enigmas. Did it truly occur? Remain with me until the very conclusion as we grapple with these disquieting questions in our inaugural novel multi-story format, designed to keep our late-night audience abreast of all cosmic developments unfolding above our heads. If these enigmas have captivated you as much as they have me, ensure you bestow a like and subscribe so you don't miss a single update. As this narrative progresses in real time, share your location in the comments, the current time there, and your conviction regarding whether we are privy to the complete truth surrounding these world-altering discoveries. And should you wish to foster the growth of this community, disseminate this video across X, Facebook, Reddit, or even within your group chats. Your support is the bedrock upon which our pursuit of such stories rests. Thus, thank you for your unwavering backing. Part 1. The Anomalous Signal. Envision this. You are suspended in the profound silence of space, more than 3 times the distance of Earth from the Sun. In this remote domain, sunlight is but a faint caress. Ice remains resolutely frozen. Comets enter a dormant state. All lies dormant. And then it becomes visible. A comet, seemingly hemorrhaging water into the void, profusely ejecting 40 kilograms of this substance into space each passing second. Not a mere dribble, but a torrent. Water cascading from a frozen mass where its presence is utterly unexpected. This is 3 Atlas, an interstellar comet that has entered our solar system from an unknown origin, carrying the celestial laws of another star's domain. And these laws, they diverge from our own. The initial revelation emerged from SWIFT, a space telescope engineered to detect gamma-ray bursts. SWIFT directed its ultraviolet gaze toward 3 Atlas in early 2025 and observed something astonishing. A luminous envelope of hydroxyl molecules encircling the comet. Hydroxyl, or OH, is the byproduct of sunlight fragmenting water molecules. It is the lingering echo of water's disintegration. The presence of OH signifies that water was recently present, and SWIFT detected a substantial quantity of it. The figures are truly astounding. At a distance of 3.51 astronomical units from the Sun, 3E Atlas was releasing 1.35 multiplied by 10 to the 27th power water molecules per second. That equates to 40 kilograms per second, every single second. To put this in perspective, it's akin to discharging the volume of a small car's worth of water into space every minute at a distance where comets from our solar system emit only a faint trace. Comets native to our solar system do not exhibit this behavior. Not in this remote region. This far from the Sun, they are frigid, inert, virtually lifeless. Water ice requires warmth to sublimate, to transition directly from a solid state to a gaseous one without liquefying. And there is simply insufficient solar energy at this distance to fuel such activity. Our comets await until they draw considerably nearer to the Sun before they awaken and commence releasing gas and dust into space. 3 Atlas did not receive that directive. You may recall Oumuamua, the inaugural confirmed interstellar visitor. That object was parched, entirely devoid of water or outgassing, merely a tumbling rock traversing our celestial vicinity. Silent. Subsequently, Borisov, arrived, the second interstellar comet. Borisov was active, certainly, but it behaved precisely as our comets do. It adhered to the established pattern. It was predictable. It was, in the most favorable sense, mundane. 3 Atlas embodies neither of these characteristics. It exhibits a vitality that defies expectation. It is vociferously expelling water into a vacuum where profound silence ought to prevail. And the singular question occupying the minds of every astronomer who has directed a telescope toward this entity is straightforward. How? What mechanism could possibly account for this phenomenon? Is there an as-yet undiscovered exotic ice? Something that sublimes at temperatures we deemed too frigid? Could the comet's interior still retain residual warmth from its formation billions of years ago? Is it rotating in an unusual manner that concentrates sunlight onto concealed reserves of volatile substances? Or is there a chemical process occurring within that celestial body that has remained entirely beyond our current understanding? The water is merely the genesis of this enigma. 3 Atlas is also shedding other constituents: cyanide, nickel, carbon dioxide in concentrations that defy logic. Each new observation adds another layer to the mystery. Each spectral signature detected in the data represents an additional unanswered question. This is not merely a comet behaving unconventionally. This is a comet seemingly operating under an entirely distinct set of physical principles. Principles established in a different star system under contrasting conditions with unique chemistry. And now it graces our solar system, granting us an unhindered view of processes previously unseen. The source of astronomers' consternation lies in this. If 3 Atlas is performing actions beyond the capabilities of our comets, what does this reveal about its place of origin? What kind of stellar system gives rise to comets of this nature? What were the ambient conditions within its protoplanetary disk billions of years ago? And most intriguingly, is this comet merely an anomaly, or is it a harbinger conveying intelligence about the universe's inherent diversity? Every available telescope is presently focused upon it. Spectroscopy, photometry, polarimetry, every instrument at our disposal. Because 3 Atlas is not merely an object of curiosity, it represents a portal, a rupture in our comprehension. And through this aperture we may glimpse something truly extraordinary. Part 2. Nickel without iron. Comets are expected to adhere to established patterns. As they absorb heat, metals begin to sublimate from their surfaces. Iron and nickel are invariably found together, akin to inseparable companions. The presence of one signifies the presence of the other. This is one of those cosmic constants upon which we have come to depend. Yet 3 Atlas appears to have disregarded the established protocol. The Very Large Telescope in Chile directed its spectrograph towards 3 Atlas and detected a phenomenon that defied explanation. Nickel emission lines were radiating with intense brilliance in the spectrum, robust, unmistakable, impossible to overlook, and iron either entirely absent or exhibiting such faintness as to be barely perceptible. Nickel unaccompanied by iron. It is akin to observing smoke without fire. It is like discovering footprints without any accompanying feet. Within our solar system, this scenario does not occur. When a comet attains sufficient temperature to release metals, iron and nickel manifest in predictable proportions due to their entanglement within identical mineral structures. They form through analogous processes. They sublimate at comparable temperatures. They are chemically bound in such a way that they remain paired. However, 3 Atlas seemingly originated from a location governed by different principles. At approximately 2.8 astronomical units from the Sun, astronomers measured nickel emanating from the comet at roughly 5 grams per second. 5 grams may not seem significant until one realizes this emission is occurring ceaselessly, second after second, with no discernible presence of iron. This is not an anomaly, it is a discernible pattern. It signifies that the comet is imparting fundamental information about its composition. Several hypotheses have been proposed, none of which are straightforward. The initial possibility is chemical fractionation. Perhaps in the environment where 3 Atlas formed, nickel became integrated into volatile compounds that vaporize readily, while iron became entrapped within refractory minerals requiring substantially higher temperatures for sublimation. Imagine nickel hitching a ride with volatile ices, while iron remained sequestered in rocky particles, leading to the observed decoupling. Another hypothesis involves organometallic compounds. On Earth, we encounter molecules such as nickel carbonyl, where nickel atoms bind with carbon monoxide. These compounds are volatile. They evaporate at relatively low temperatures. If 3 Atlas originated in an environment rich in carbon monoxide and other organic substances, it's conceivable that nickel became ensnared within such molecular structures. When sunlight interacts with them, they decompose, releasing atomic nickel into the comet's coma, while iron remains bound within solid grains. Then there is space weathering. Cosmic rays and ultraviolet radiation bombard interstellar objects for millions or billions of years. Such sustained exposure can alter surface chemistry in peculiar ways. It's possible that radiation processing has generated nickel-rich surface layers, while iron has been either buried or chemically transformed. Perhaps the nickel we are observing is a superficial layer, a rind altered by radiation that does not accurately reflect the comet's true bulk composition. Or, and this is the most compelling possibility, 3 Atlas formed within a stellar system exhibiting genuinely divergent elemental abundances. Stars do not all possess the identical chemical makeup. Older stars, stars originating from different galactic sectors, stars that coalesced from nebulae enriched by diverse supernova events. Each possesses a unique elemental composition. It's plausible that 3E Atlas originates from a locale where nickel was more prevalent in proportion to iron than in our immediate vicinity. Perhaps its parent star possessed an unusual chemical signature, and that peculiarity is now imprinted upon every molecule of this comet. However, caution is warranted here. Spectroscopy presents challenges. Detecting faint emission lines against a luminous backdrop is intricate. There are limits to detectability. It is possible that iron is present, but below the threshold of detection. The iron emission might be superimposed upon other spectral features. We might be examining the incorrect wavelengths. As the comet draws nearer to the sun and its temperature increases, iron might begin to manifest. This would, in a sense, be reassuring. It would signify that the universe remains comprehensible. But what if it does not? What if 3 Atlas reaches perihelion, its closest point to the sun, and iron remains conspicuously absent? What if the nickel-to-iron ratio persists in a completely inverted state compared to all our prior observations? That would be revolutionary. It would indicate that planetary systems can produce comets with metallic chemistry so dissimilar to ours that our current models would necessitate complete reevaluation. This is precisely why astronomers are observing 3 Atlas with such intense scrutiny. Each observation serves as a test. Every spectrum presents an opportunity to either validate our understanding or shatter it. And at present, 3 Atlas is contributing more to the shattering than to the confirmation. Part 3. A comet that activates. Comets are expected to gradually increase in brightness as they approach the sun. The underlying physics is straightforward. Increased solar radiation leads to heightened temperatures, enhanced sublimation, and consequently, a greater outflow of gas and dust. This relationship should be continuous, predictable, and almost uneventful. 3E Atlas, it seems, also missed that particular directive. Observers monitoring 3E Atlas noted a peculiar characteristic in its coloration. Initially, the comet appeared relatively neutral, perhaps with a slight reddish hue, typical of distant icy bodies. However, as it approached its closest proximity to the Sun, it began to adopt a green coloration. This was not a subtle shift, but a vivid spectral green that became undeniably apparent in photographic records. This green hue originates from two distinct sources, cyanide molecules and atomic nickel. Both emit strongly within the green portion of the electromagnetic spectrum, and both began to intensify dramatically as the comet warmed. The increase in brightness was not linear. It was not a smooth progression. It was demonstrably superlinear, indicating that the emission lines were escalating at a rate exceeding what simple geometric principles would predict. When considering the distance from the Sun, one expects 4 times the solar radiation per square meter, according to the inverse square law, a fundamental principle of physics. Yet, the emissions from 3 Atlas were increasing at an even more rapid pace. Something was being unlocked. A novel process was initiating. Astronomers refer to this as switch-on behavior. Imagine a temperature threshold. Below this threshold, a specific ice remains solid, locked away, inert. Then, as the comet crosses this threshold, that ice unexpectedly begins to sublimate. Gas production surges. New emission lines appear in the spectrum. It is akin to activating a switch. One moment the process is inactive, the next it is engaged. And once activated, it can escalate uncontrollably if there is a sufficient supply of material to sustain it. 3. Atlas appears to possess multiple such switches. The water initiated its release first, at a distance of 3.5 astronomical units, which is already anomalous. Subsequently, the cyanide and nickel commenced their emission, manifesting as a vivid green as the comet's temperature further increased. Each emission suggests the tapping of a distinct volatile reservoir, a different chemical environment reaching its activation point. One model that could elucidate this phenomenon involves dispersed icy grains within the coma. Instead of all activity originating from the nucleus's surface, envision small ice particles being ejected from the nucleus by escaping gas. These particles drift away from the comet, remaining cold and frozen. However, as they travel, they are increasingly exposed to sunlight. Eventually, each individual grain reaches its unique threshold and begins to sublimate. This creates a distributed source of gas, not solely emanating from the nucleus, but from a cloud of icy particles surrounding it. This could account for the superlinear increase in brightness and the sudden appearance of new emission lines. Another possibility is thermal fracturing. Comets are essentially composed of dirty ice and rock. When one section heats up and expands while another remains cold and contracted, internal stresses accumulate. Ultimately, a fracture occurs. When ice fractures, it can expose fresh material that was previously shielded. Abruptly, new surface area becomes available for sublimation, and new volatiles are released. The comet experiences an outburst. 3E Atlas may be fracturing itself as it warms, revealing successive layers of frozen chemistry. Then there are the exotic ices. Water ice sublimes at one temperature. Carbon monoxide ice sublimes at a significantly lower temperature. Carbon dioxide's sublimation point lies somewhere in between. If 3E Atlas is structured in concentric layers, akin to an onion, with different ices residing at varying depths or within distinct regions, then as it warms, a sequence of activations would be observed. First, the highly volatile substances, followed by the standard volatiles, and finally, the more recalcitrant materials. Each layer peeling back like chapters in a narrative. This is not entirely foreign to our experience. We have witnessed comets within our solar system exhibiting unusual behavior. Some comets undergo sudden outbursts, experiencing a tenfold or greater increase in brightness overnight. Some comets fragment as they approach the Sun, with thermal stresses overwhelming their structural integrity. Some comets remain dormant until very close to perihelion and then erupt into activity. However, 3 Atlas is exhibiting this behavior on a timescale that deviates from our observations. It is active at distances where it should be quiescent. It is activating in ways that seem almost intentional, and the anticipation is mounting. As 3 Atlas continues its inward trajectory, will further switches be triggered? Will we observe the appearance of new emission lines, new molecules we did not anticipate? Will the activity reach a plateau, or will it continue to accelerate? Each week brings fresh data and novel surprises. This is not a comet that follows a steady, predictable course. This is a drama unfolding in real time. Part 4. Its origin. Every celestial object carries a narrative inscribed within its trajectory. Its future path reveals its past, and the trajectory of 3 Atlas tells a story spanning billions of years and thousands of light years. The orbit is hyperbolic. This is the technical designation for an open curve, a path that does not loop back upon itself. 3 Atlas originated from interstellar space, executed a maneuver around the Sun, and will depart once more, never to return. Its eccentricity exceeds 1, signifying that this comet is unbound, an independent entity, a wanderer. It is merely passing through. Astronomers traced its path backward using pre-discovery images. Recovery involves searching archival survey data for images of an object before its significance was recognized. It transpired that 3 Atlas had been photographed on multiple occasions by automated surveys. Some images dated back to when the comet was 6.4 astronomical units distant, still approaching, still cold and remote. By piecing together these observations, astronomers meticulously reconstructed its trajectory with increasing accuracy. And that trajectory points outward, back into the galaxy, but not to just any location. Orbital modeling, coupled with data from the Gaia Space Telescope, which has meticulously charted the positions and movements of billions of stars, enables astronomers to formulate informed hypotheses regarding 3 Atlas's potential origin. The conclusion is surprising. The galaxy possesses a defined structure. The stars are not distributed randomly. The majority of stars, including our Sun, reside within the thin disk, a comparatively planar region of younger, metal-rich stars orbiting the galactic center. However, there is also a thick disk, comprising an older population of stars that follow more inclined, more eccentric orbital paths. These thick disk stars are vertically expanded, extending further above and below the galactic plane, and they exhibit distinct chemical compositions. They are older, having formed earlier in the galaxy's history when fewer heavy elements were present. They possess lower metallicity. The trajectory of 3 Atlas suggests it may have originated from the thick disk. If this is the case, if this comet formed within that ancient stellar population, then it could predate our solar system. Our solar system is 4.6 billion years old. Thick disk stars can be 7 billion years old or more. This implies that 3 Atlas could be carrying ice and rock from a period before the Sun itself existed. Consider the chemical implications of this. The gaseous cloud that collapsed to form a thick disk star 7 billion years ago contained fewer heavy elements than the cloud that gave rise to our Sun. Supernova explosions enriched the galaxy over time, seeding it with elements heavier than helium. The earliest stellar generations consisted almost exclusively of hydrogen and helium. Later generations, like our Sun, contain a few percent of heavy elements interspersed. Stars within the thick disk represent an intermediate stage. They contain some heavy elements, but fewer than we do. If 3 Atlas formed in such an environment, its composition would reflect that reduced metallicity. There would be less iron, less magnesium, less silicon. all the rocky elements that constitute planets, but there would still be an abundance of volatiles, carbon, nitrogen, oxygen, bound within ices and molecules. Perhaps this explains the exceptionally high ratio of carbon dioxide to water. Perhaps it accounts for the anomalous metallic ratios. It is conceivable that this comet is a chemical relic from a time when the galaxy was younger and the periodic table was less populated. Naturally, certainty remains elusive. Tracing an object's path back through billions of years of galactic movement is a complex endeavor. Gravitational influences from passing stars and interactions with the galaxy's spiral arms introduce uncertainties into the historical reconstruction. However, the mere plausibility that 3 Atlas predates our solar system is extraordinary. We may be observing a relic, a survivor, a time capsule from the ancient galaxy. And should we be able to pinpoint its stellar nursery, the group of stars that formed together from the same gaseous cloud, we might one day identify its siblings. Other comets, perhaps even planets, ejected from the same system, now dispersed across the galaxy. 3 Atlas might be a single character in a message written across thousands of light years, and we are just beginning to decipher its meaning. Part 5. What is it carrying? Comets are more than just ice and rock. They function as transport vessels, carrying the molecular inventory of their place of origin. And 3E Atlas is transporting some remarkably peculiar cargo. We have already discussed the water, 40 kilograms per second, flowing into space at distances where such an outflow should be impossible. That water, or rather the hydroxyl fragments left behind when sunlight disassociates it, was the initial indicator of this comet's unusual nature. However, water represents merely the commencement of this revelation. Carbon dioxide is the true surprise. Observations suggest that 3 Atlas possesses an exceptionally high carbon dioxide to water ratio. In comets within our solar system, water typically predominates. It serves as the primary volatile, the principal driver of activity. Carbon dioxide is present, certainly, but it occupies a secondary role. 3 Atlas reverses this dynamic. Certain observations indicate that 95% of the gaseous releases are carbon dioxide, with water vapor present in lesser quantities. This deviates significantly from our typical understanding. It's an unexpected composition. Why would a celestial body of this nature be so rich in carbon dioxide? One potential explanation relates to its formation temperature. Carbon dioxide ice solidifies at warmer conditions compared to water ice. If the object in question, designated as 3I Atlas, coalesced within a hotter zone of its nascent planetary disk, closer to its progenitor star, it might have preferentially gathered carbon dioxide while shedding some of its water content. Alternatively, the radiation environment of its parent star could have been different, influencing the ice composition in ways our Sun does not. Another possibility involves the system's giant planets, if any existed. Their migration patterns might have differed, agitating the disk and intermingling materials in unforeseen ways. Then there's the presence of cyanide. Cyanide, or CN, is a common constituent of comets, responsible for the characteristic green hue observed in many. However, in 3I Atlas, the cyanide appeared subsequent to the water, later in the warming process. In comets originating from our solar system, cyanide and water tend to emerge concurrently due to their similar sublimation temperatures. The delayed appearance of cyanide in 3I Atlas suggests it might have been sequestered differently. Perhaps it was embedded within organic molecules that required additional energy to decompose, or it could have been frozen in layers beneath the water ice. And of course, there's the atomic nickel emitting a green glow, detached from its usual partner, iron. While this particular enigma has been previously investigated, its significance warrants reiteration. Every element and molecule detected serves as a crucial piece of evidence. Volatile compounds provide insights into the temperature and pressure conditions during formation. Refractory materials reveal details about condensation sequences and thermal processing. The ratio of gas to solid particles offers clues about the comet's structural integrity and its susceptibility to disintegration. Now, let us address the prevailing topic, the panspermia hypothesis. This concept posits that life, or at least the fundamental components of life, can disseminate across the cosmos via comets and asteroids. 3I Atlas possesses water, organic compounds, and cyanide, a key precursor in prebiotic chemical reactions. If one were to engineer a comet with the express purpose of seeding a planet with interesting chemistry, it would invariably contain precisely these constituents. However, it is imperative to state unequivocally that this remains purely speculative. There is absolutely no evidence to suggest that 3I Atlas is carrying life, nor is there any evidence that any comet has ever harbored life. The panspermia hypothesis, while intriguing and theoretically plausible, remains unproven, and it faces considerable challenges. The harshness of cosmic radiation is a significant obstacle. Over millions of years traversing interstellar space, high-energy particles relentlessly degrade complex molecules. Stellar ultraviolet radiation exerts a similar destructive effect. Essential biological molecules like DNA and proteins, and even simple amino acids, are vulnerable to disintegration. For life to endure an interstellar voyage, it would need to be deeply shielded within the comet's interior, protected by substantial thicknesses of ice and rock. However, complex organic molecules themselves might survive, not as living organisms, but as chemical remnants. These molecules could have been synthesized within the comet's parent system, perhaps in a planetary atmosphere or on its surface, and subsequently incorporated into the comet. Such molecules could withstand the journey if they possess sufficient stability and adequate protection. Analyzing them could unlock information unattainable through other means. They might illuminate atmospheric chemistry from an extraterrestrial world. They could reveal metabolic pathways from an extinct biosphere. They might serve as coded messages in carbon, nitrogen, and oxygen, awaiting decipherment. This is precisely why certain scientists harbor aspirations of intercepting one of these interstellar travelers, not merely observing it from Earth, but dispatching a spacecraft to match its velocity, to land upon it, to extract samples through drilling and analysis. The technological hurdles are immense. Interstellar objects traverse at considerable speeds, measured in tens of kilometers per second. Intercepting one would necessitate a spacecraft already in position or possessing extraordinary acceleration capabilities. Yet the scientific rewards would be immeasurable. A sample from another star system, chemical signatures from a distant galactic region, answers to questions we have only just begun to formulate. 3I Atlas is already billions of kilometers distant from the inner solar system. We missed the opportunity to intercept it this time, but it serves as a potent illustration of what is achievable. It demonstrates the existence of phenomena beyond our solar system, igniting a desire for further exploration. Part 6. Citizen Scientists Capturing Spectral Phantoms. Occasionally, the most significant discoveries emerge when data is examined with a unique perspective, not through automated processes or machine learning, but through human perception and intuition. Furthermore, such breakthroughs can arise from individuals who are not professional astronomers. Allow me to introduce the concept of odd radio circles, or ORCs. If you are unfamiliar with them, you are not alone. Their discovery dates back to 2019, making them remarkably novel in astronomical terms. These are vast, ring-like structures discernible only in radio wavelengths. They are invisible to optical telescopes and infrared detection. Directing a radio telescope towards a specific region of the sky reveals their presence. perfect circles of radio emission, sometimes spanning hundreds of thousands of light years, suspended in space like ethereal cosmic smoke rings. Their origin remains a mystery. The prevailing theory attributes them to galactic winds or shock waves emanating from supermassive black holes. But in truth, the investigation is ongoing. They are genuinely enigmatic, and their detection is challenging due to their faintness and their tendency to blend with the general radio background. Automated detection algorithms often overlook them, as they are optimized for identifying point sources or concentrated objects, rather than diffuse, expansive rings. Enter Zooniverse. This initiative enlists volunteers to visually scrutinize radio continuum maps, searching for anomalies. Participants are not seeking any specific phenomenon. They are looking for the unusual. In March of 2025, a volunteer identified something extraordinary. The celestial object, catalogued as Ray J 31346, 503 TU, possesses a rather unmemorable designation, but its nature is far more captivating. It is a pair of intersecting radio rings, two circular structures overlapping in the sky to form a figure-8 configuration. This represents the most distant and most powerful ORC discovered to date, identified not by an algorithm or a professional survey, but by an individual contributing their time to scrutinize data. The discovery was made utilizing low-frequency continuum maps from the Low-Frequency Array, LOFAR, a radio telescope network distributed across Europe. LOFAR generates an immense volume of data, far exceeding the capacity of professional astronomers to manually examine. Automated processing pipelines handle the majority of this data, flagging potential objects based on characteristics such as brightness and shape. However, these pipelines incorporate filters and thresholds designed to identify expected phenomena rather than the unexpected. This is where human pattern recognition proves invaluable. Our brains are exceptionally adept at perceiving deviations from the norm, discerning structure within apparent randomness, and identifying something as noteworthy even without a clear articulation of why. The volunteer who discovered RAJ in 31346 503 TU did not need to comprehend the physics of ORCs. They merely had to observe the image and recognize its peculiarity. Their intuition proved correct. This is not an isolated incident. Zooniverse has facilitated the flagging of numerous anomalies. Another volunteer identified a colossal radio galaxy encircled by a distinctive ring structure. Yet another detected a ring at the terminus of a jet, a feature not predicted by theoretical models. These are objects that would have been lost amidst the data deluge had human observers not been involved. This situation offers a broader lesson extending beyond radio astronomy. We are entering an era of unprecedented data volume. The Vera C. Rubin Observatory, upon its operational commencement, is projected to generate 15 terabytes of data nightly. This amounts to 15 terabytes every single night for a decade. No human team can possibly review all of it. No suite of algorithms can capture every anomaly. We require both, machines to manage the bulk processing and humans to identify the unusual outliers that defy existing frameworks. Let us now draw a parallel to 3I Atlas. Could a citizen scientist have identified its anomalies earlier? Might someone scrutinizing spectral data have noted the nickel signature in the absence of iron before professional astronomers did? Could an individual monitoring cometary activity have inquired, why is this object exhibiting activity so far from the sun? Perhaps, perhaps not. However, the fundamental point is that anomalies such as those observed in 3I Atlas benefit from the broadest possible scrutiny of the available data. Professional astronomers possess expertise, training, and context, but they also operate with preconceived notions, models they aim to validate, and time constraints. Amateurs and citizen scientists bring fresh perspectives. They are not bound by pre-existing expectations and are therefore free to observe what is actually transpiring. There are documented instances of amateur astronomers discovering supernovae, locating asteroids, and tracking variable stars. The Japanese amateur astronomer Yuji Nakamura discovered multiple comets and a supernova. The British amateur Andrew Gray co-discovered an unusual stellar outburst. These are not mere coincidences. They exemplify the outcomes when passionate individuals, equipped with telescopes or data access, dedicate themselves to careful observation of the universe. In the future, as telescopes inundate us with petabytes of data, citizen scientists may well become the initial responders to cosmic anomalies, identifying the next interstellar comet, the next peculiar radio formation, or the next phenomenon that defies current understanding. Subsequently, professional astronomers will conduct follow-up investigations to elucidate the underlying physics. This constitutes a collaborative partnership, and like all effective alliances, it is more robust than the sum of its individual components. Part 7. Citizen Science versus Professional Gatekeeping. However, it is important to acknowledge that this collaborative landscape is not without its complexities and inherent tensions. The integration of citizen science introduces challenges, including an increase in false positives stemming from well-intentioned amateurs who identify phenomena that ultimately prove to be instrumental artifacts or background noise. Furthermore, there are individuals who, motivated by conspiracy theories, interpret every data anomaly as evidence of extraterrestrial signals. Professional astronomers, understandably, express concerns regarding these issues. Organizations such as the Royal Astronomical Society and similar bodies have engaged in extensive deliberation on this matter. On one hand, citizen science alleviates data processing backlogs, enabling projects to analyze a greater volume of data than would otherwise be feasible. It also fosters public engagement and cultivates enthusiasm for scientific pursuits. On the other hand, rigorous quality control is paramount. A discovery is not considered validated until it has undergone verification, cross-checking, and peer review, processes that demand considerable time and expertise. False positives present a genuine challenge. An individual flags an object as unusual, prompting astronomers to dedicate days or weeks to follow-up investigations, only to conclude that it is instrumental noise, a satellite trail, or a cosmic ray impact. This diverts valuable time that could otherwise be allocated to genuine discoveries. The accumulation of false positives can lead to skepticism among astronomers regarding citizen reports, diminishing the signal-to-noise ratio and fostering fatigue. Moreover, confirmation bias can influence perception. Individuals seeking specific patterns may inadvertently perceive them even in their absence. While this phenomenon affects professionals as well, peer review and established protocols serve as essential checks. Amateurs may lack these safeguards and might interpret random data patterns as significant, leading to unsubstantiated claims, such as those concerning alien megastructures around Tabby's star or purported messages embedded within pulsar timing residuals. Calibration and error margins represent another area of concern. Professional astronomers possess the expertise to assess measurement uncertainties and differentiate statistically significant signals from noise. Amateurs may lack this proficiency and might report detections that are merely minor statistical fluctuations devoid of broader significance. Furthermore, bandwidth limitations can arise. If a citizen science project garners excessive popularity, leading to a surge in flagged objects, the professional astronomers responsible for follow-up investigations may become overwhelmed. Their capacity to investigate every submission is finite, necessitating prioritization, which could result in genuine discoveries being overlooked due to the sheer volume of reports. Nevertheless, these challenges are not insurmountable. They represent obstacles rather than definitive impediments. The implementation of structured training protocols can mitigate these issues. By educating citizen scientists on data quality assessment, artifact recognition, and uncertainty estimation, the rate of false positives can be significantly reduced. Mentorship programs wherein experienced amateurs guide novices can help maintain scientific standards. A tiered validation system requiring multiple independent volunteers to flag the same object before it is escalated for professional scrutiny can effectively filter out spurious detections. The potential benefits are substantial. Crowdsourcing anomaly detection allows for more thorough examination of extensive data sets. Independent verification by numerous individuals minimizes the likelihood of a genuine anomaly being missed due to an individual's oversight. Diverse perspectives can lead to the identification of patterns that specialists might overlook. Returning to the case of Three-Eye Atlas, could a citizen astronomer have flagged its peculiar nickel anomaly earlier? The spectral data is publicly accessible, allowing anyone with the requisite software to download and analyze it. However, spectroscopy is a complex discipline, demanding an understanding of line identification, wavelength calibration, and signal-to-noise assessment, making it unsuitable for casual examination. Yet, with appropriate training, guidance, and a collaborative community, it is conceivable that someone might have detected the anomaly prior to its widespread recognition. The same applies to its water production rate. Light curves, which measure brightness over time, are frequently compiled by amateur astronomers. If these amateurs had been examining ultraviolet data from the Swift Observatory and had been trained to identify unusual activity patterns, they might have flagged the superlinear brightening exhibited by Three-Eye Atlas. They could have observed, "This behavior deviates from that of a typical comet," before professional surveys confirmed it. Past discoveries spearheaded by citizen scientists provide ample evidence of this potential. The transit method for exoplanet detection, which involves observing slight dimming of a star's brightness as a planet passes in front of it, has been significantly advanced by citizen scientists analyzing Kepler data. Projects like Planet Hunters have led to the confirmation of numerous exoplanets. Amateur asteroid hunters have identified near-Earth objects that eluded professional surveys. Amateur nova hunters frequently achieve discoveries of stellar outbursts before professionals, as they conduct nightly observations with smaller telescopes, whereas professional telescopes are scheduled months in advance. The conclusion is not that amateurs should supplant professional astronomers, which would be an absurd proposition. Rather, it is that both are indispensable. Professionals provide deep expertise, theoretical frameworks, and rigorous validation. Citizen scientists contribute broad observational coverage, fresh perspectives, and a multitude of observational eyes. This is not a competition, but a partnership, and in the current era of overwhelming data, it is an essential partnership. Part 8. The Coincidence Effect. October of 2025 presented a unique celestial panorama. Conditions were exceptionally favorable for observing both Mercury and Ceres. Mercury, the solar system's innermost planet, achieved an advantageous evening alignment, appearing bright and elevated above the horizon shortly after sunset. Ceres, the most substantial object within the asteroid belt, reached opposition, positioning it directly opposite the Sun in the sky, thereby appearing at its brightest and closest proximity to Earth. On social media platforms, individuals began to draw connections. Mercury was visible, Ceres was visible, and concurrently this peculiar interstellar comet, Three-Eye Atlas, was exhibiting activity. Were these events related? Was some grand cosmic alignment unfolding? Did the gravitational forces of the solar system somehow influence or amplify the comet's behavior? To be unequivocally clear, the answer is no. There is no discernible connection. Mercury's orbital path has no bearing on the outgassing of an interstellar comet. Ceres's positional relationship to Earth exerts no influence on chemical processes occurring billions of kilometers away. These are independent occurrences, coincidentally observable at the same time, and nothing more. However, humans possess an innate inclination for pattern recognition. We are wired to identify them. This is a fundamental survival trait. Our ancestors who recognized that certain berries induced illness and that specific animal tracks indicated the presence of prey were more likely to survive than those who failed to discern such patterns. Consequently, our brains are hypersensitive to patterns, sometimes to the extent of perceiving them where none exist. This phenomenon can be described as cosmic scale pareidolia. Pareidolia is the psychological tendency to perceive familiar patterns, such as faces, in random or ambiguous stimuli like clouds or static. It represents a misapplication of pattern detection. Such occurrences are common with celestial events. Ancient civilizations interpreted planetary alignments as omens. The appearance of a comet during a battle was seen as a sign of divine displeasure. The congregation of planets in a particular celestial sector was believed to portend the birth or demise of monarchs. The year 1910 provides a pertinent historical parallel. This was the year Halley's Comet returned, traversing the inner solar system on its 76-year orbital cycle. The public response was one of widespread terror. Astronomers had detected cyanogen, a toxic gas, within the comet's tail. Newspapers published sensational headlines proclaiming, "Comet's poisonous tail will pass over Earth." In response, people purchased gas masks, and some hermetically sealed their windows. There were even reports of suicides among individuals convinced the comet's passage would be fatal. Naturally, no adverse consequences materialized. The comet's tail is extraordinarily diffuse, essentially a hard vacuum by terrestrial standards. The quantity of cyanogen that actually reached Earth was negligible and undetectable. The comet posed no threat. However, the coincidence of the comet's appearance with other unrelated events, such as solar activity, political unrest, and seismic events, fueled the panic. People established connections between disparate phenomena. We are currently witnessing a similar phenomenon with 3I Atlas. The comet itself is exhibiting unusual characteristics, genuinely anomalous behavior. Mercury and Ceres happen to be visible concurrently, leading to the construction of speculative narratives. Perhaps the comet's activity is being stimulated by some form of solar system resonance. Perhaps its trajectory is being subtly altered by gravitational perturbations. Perhaps this is all part of a larger, yet to be understood cosmic pattern. Astronomical calculations have definitively established that Mercury's gravitational influence on an object in the outer solar system is virtually non-existent. Mercury is a relatively small planet, only marginally larger than our Moon, and it is situated at a considerable distance. Ceres is even smaller and exerts even less gravitational influence. The combined gravitational pull of all the planets in the solar system would be insufficient to significantly alter 3I Atlas's behavior at the observed distances. The comet's observed activity is attributable to internal processes, solar radiation, and its intrinsic composition, not to the positional alignment of Mercury in its orbit. However, factual accuracy does not always prevail when compelling narratives take hold. The human brain has an inherent craving for stories. We desire connections between events, as isolated occurrences can feel random, chaotic, and devoid of meaning. If the comet's activity is linked to planetary positions, it implies order, predictability, and significance. Conversely, if they are unrelated, it suggests a universe where strange events occur spontaneously, a notion that can be psychologically unsettling. Confirmation bias exacerbates this effect. Once an individual begins searching for connections, they tend to find them ubiquity. For instance, Mercury was also visible during a previous comet discovery. Ceres was near opposition when another unusual object was identified. This overlooks the fact that Mercury is visible multiple times a year, and Ceres reaches opposition annually. It also disregards the constant stream of unusual astronomical discoveries. The brain selectively retains coincidences that reinforce a narrative while disregarding contradictory information. Social media amplifies this phenomenon exponentially. In bygone eras, a theory positing planetary alignments influencing comets might have been shared among friends, who would likely dismiss it as nonsensical, effectively concluding the matter. Today, such a theory can be disseminated online, instantly connecting the originator with a community of like-minded individuals. Links, images, and charts illustrating alignments are exchanged. New evidence is added by participants, and the information is further propagated. Consequently, a comprehensive alternative narrative emerges, competing with the established scientific explanation. The fundamental takeaway isn't that individuals are unintelligent or easily deceived. Instead, it highlights how impactful coincidences can be, and how our cognitive processes are not finely tuned to disregard them. Given the sheer volume of astronomical occurrences happening constantly, it's statistically inevitable that some will align purely by chance. These fortunate alignments will appear significant, even when devoid of true meaning. This insight is crucial because it influences how people interpret unusual phenomena, such as the comet Three-Eyed Atlas. When one is predisposed to perceive cosmic patterns or believes that celestial alignments hold sway, the comet's peculiar behavior becomes evidence of something grander. Perhaps it is not a naturally occurring comet at all. Perhaps it is of artificial origin. Perhaps it is reacting to planetary transmissions. Perhaps it is a component of some vast, incomprehensible cosmic mechanism. This leads us to an even more perplexing segment of this narrative. We delve into the mechanics behind fabricated events, speculative theories, and the human tendency to transform scientific enigmas into cultural legends. This is Part 9, an update from October of the year 2025. Was it even real? October 8th, 2025. Blue Origin's mission NS-36. 6 individuals on board for 11 minutes. One clandestine passenger whose identity remained concealed until the spacecraft's final touchdown. The capsule ascended, breached the Kármán line, experienced weightlessness, began its descent under parachutes, and ultimately landed in the Texan desert. A successful endeavor. Another impeccable flight for the company's space tourism initiative. This marked their 15th crewed mission. A routine operation, almost. That's the official account. News outlets like ABC News reported on it. A publication called Medium featured an article. A few specialized space journalists shared updates on social media. The identity of the mystery passenger was disclosed following the landing. It was a private citizen who had requested anonymity during the flight, but was amenable to being named afterward. This is not an uncommon occurrence. Individuals frequently opt for privacy and are willing to reveal themselves later. However, this is where the peculiarity arises. This is what continues to trouble anyone closely following spaceflight. The pervasive silence. An unsettling, almost suffocating lack of widespread reporting. There were no viral videos, no trending hashtags, no celebrity endorsements or humorous internet memes, and no in-depth analyses on platforms like TikTok. A spaceflight, a commercial journey into the fringes of space, something that, mere years prior, would have dominated headlines for an extended period. Instead, it registered as a mere blip. Take a moment to consider this. 6 human beings departed Earth. They experienced weightlessness, witnessed the planet's curvature against the void of space, and returned safely. This is an extraordinary feat. It should be extraordinary. Yet the internet seemed indifferent. Social media moved on within hours. The story dissipated like mist. Why? Why so little documentation? Blue Origin typically releases footage from within the cabin. These are often beautiful shots of passengers floating, laughing, and gazing out the windows. Where was that footage? Why wasn't it plastered across every news platform? Why didn't the revelation of the mystery passenger generate widespread curiosity? Who were they? Why did they desire anonymity? These are natural inquiries, the kind that typically ignite days of speculation and public interest. Instead, there was nothing, a deafening silence. It is as if the flight transpired in a void, not only of space but also of public attention. And this void, this absence, begins to feel like a form of presence in itself. The silence becomes more resonant than any proclamation could be. You begin to ponder. You start to pose uncomfortable questions. Did this flight truly unfold as reported? Were there indeed 6 individuals on board, or was the passenger manifest different? Was the mystery passenger a genuine person or a narrative construct to explain the lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was footage from a prior mission re-edited with a new date? These are paranoid notions, the hallmarks of conspiratorial thinking, the kind of reasoning that perceives threats in every shadow and trusts nothing. Yet, at times, the lack of evidence itself feels significant. When something that should command attention remains conspicuously quiet, an explanation is warranted. Let us contrast this with the events of April of the year 2025. Merely 6 months prior, Blue Origin conducted another New Shepard mission, and that one ignited public fascination. Not due to any malfunction, but because of its passengers. Celebrities like Katy Perry and Gayle King, comprising the first all-female crew, were high-profile individuals with millions of followers. This was the kind of flight engineered to generate headlines, and it certainly did. However, not in the manner Blue Origin might have anticipated. Within hours of the live broadcast concluding, social media was inundated with conspiracy theories. Individuals asserted that the flight had been staged. They meticulously analyzed every frame of the footage, searching for inconsistencies. The behavior of hair in zero gravity became a subject of intense forensic scrutiny. Did it float correctly? Did it move too rigidly? Was it genuine hair, a wig, or digitally generated? The capsule's hatch also became a focal point. Someone claimed it opened differently than in previous missions. They presented side-by-side comparisons, added arrows, and highlighted ostensibly anomalous details. Wasn't the latch on the opposite side previously? Didn't the door swing outwards before? Why does this appear dissimilar? Then the truly outlandish claims emerged. Allegations of green screen technology, assertions that the passengers were filmed in a studio with artificial windows displaying pre-recorded footage of Earth, accusations that hands resembled those of mannequins, too smooth, too artificial. Complaints were raised about the absence of visible scorch marks on the capsule following re-entry. Every minute detail was interpreted as proof of deception. Journalists systematically debunked these claims. Hair behaves unusually in microgravity because gravity does not pull it downwards, allowing it to respond to air currents, static electricity, and random movements. The hatch mechanism is identical across all flights. Camera angles and lighting can alter its appearance. Reflections in visors can distort perspective. Scorch marks are not always discernible, depending on the dust coverage at the landing site and the camera's resolution. However, these debunking efforts did not quell the theories. If anything, they intensified them. Those inclined to believe the flight was fabricated interpreted the debunking as a cover-up. They delved deeper, uncovering more perceived evidence and constructing elaborate scenarios of how the hoax was executed. The conspiracy theory became self-perpetuating. Now we have 2 missions, both utilizing the same rocket and a similar operational profile, separated by 6 months. One generated an uproar of attention and skepticism, while the other barely caused a ripple. And one must ask, Which scenario is more indicative of suspicion? Part 10. Celestial Enigmas as Reflections. The cosmos consistently presents us with unexpected phenomena, objects that defy classification, signals that lack discernible meaning, and events that contradict our carefully constructed scientific frameworks. In every instance, without fail, we undertake two actions. First, we diligently strive to comprehend the scientific underpinnings. Second, we project our own interpretations onto these mysteries. Consider Oumuamua, observed in 2017. It was the first confirmed object from beyond our solar system to traverse our celestial neighborhood. It tumbled, exhibited a reddish hue, was elongated in shape, and notably it accelerated as it departed. While the acceleration was not substantial, it was measurable. This outward acceleration did not align with a purely gravitational trajectory, suggesting an external force was propelling it. Scientists proposed outgassing, the release of volatile substances that, in small amounts, could generate thrust akin to a weak comet, even though no gas was directly detected. Alternatively, it might have been a hydrogen iceberg, frozen H2, which would sublimate invisibly. Another possibility posited was a fragment from a shattered planet, whose shape and rotation created radiation pressure effects. However, a segment of individuals, including some scientists, put forth an alternative hypothesis. What if Oumuamua was artificial? A light sail, a solar sail, a thin membrane being propelled by the pressure of starlight. This would readily explain its acceleration, and if it were artificial, it could potentially be a probe dispatched by another civilization, perhaps engaged in exploration, or perhaps a derelict artifact from a long-vanished alien society. A similar situation arose with Tabby's star, KIC 846 2852. This star, observed within the Kepler field of view, displayed peculiar dimming patterns, characterized by deep, irregular fluctuations in its brightness, sometimes decreasing by 20% or more. Such a phenomenon could not be attributed to a planet, as no planet is large enough to obscure such a significant amount of light. Furthermore, the dimming events did not occur at regular intervals, as would be expected from a planet transiting its star. Astronomers hypothesized clouds of dust, swarms of comets, or debris resulting from a planetary collision. However, one paper, presented somewhat facetiously, suggested the presence of an alien megastructure, a Dyson swarm. This would entail millions of solar panels or habitats orbiting the star to harness its energy, leading to irregular light blocking as these structures moved. This hypothesis, to some extent, aligned with the observed data. Odd radio emissions, fast radio bursts, the enigma of three-eyed Atlas. Every unexplained phenomenon becomes a canvas upon which we project our hopes and fears. Are we alone? Is the universe indifferent or purposeful? Do other sentient beings exist? And if so, are they akin to us or unfathomably alien? The underlying psychology at play is profound. Pareidolia, the propensity to perceive patterns in random data, is a contributing factor. We discern faces in clouds, hear voices in static, and interpret intelligence in astronomical anomalies. This is not an indication of ignorance. It is a fundamental aspect of how our brains operate. We are, in essence, pattern recognition machines, and we exhibit a bias towards identifying false positives. It is more advantageous to mistake a shadow for a predator than to overlook a genuine predator as a mere shadow. There is also an inherent existential longing. We crave connection. We desire the reassurance that we are not the sole sparks of consciousness adrift in a vast, indifferent cosmos. Every anomaly represents a potential opportunity, a possibility, a gateway that might lead to something extraordinary. Consequently, we vigorously explore these possibilities. Three-eyed Atlas serves as a mirror. Within its luminous green aura, we see reflected our own inquisitiveness, our profound desire for meaning, and our hope that the universe is more mysterious and wondrous than we currently imagine. And perhaps it is. It is conceivable that one day we will encounter something genuinely inexplicable, something that compels us to rewrite the laws of physics or to accept the reality of our not being alone. However, that epoch has yet to arrive. For the present, we are observing a comet. A peculiar comet, a fascinating comet, but likely still just a comet. And that, in itself, is sufficient, because even the mysteries presented by nature are extraordinary. Part 11. The Cosmic Library of Stellar Systems. Envision the galaxy as an immense repository of knowledge, not a collection of books, but rather of celestial bodies. Comets, asteroids, rogue planets ejected during the tumultuous formation of planetary systems and subsequently cast into interstellar space. Each of these objects acts as a message in a bottle, carrying information about the stellar system from which it originated. Occasionally, one of these vessels washes ashore on our cosmic beach. Such is the nature of interstellar objects. They are, in essence, postcards from distant stellar systems. Not alien in the sense of extraterrestrial intelligence, but rather alien in their foreignness, their distinctness, having formed under conditions dissimilar to those within our own solar system. Every interstellar object we detect provides a data point, a singular sample. With a sufficient quantity of such samples, we can begin to grasp the diverse chemistries of planetary systems. The comets native to our solar system exhibit a considerable degree of uniformity. They originated within the same protoplanetary disk, coalescing from similar well-mixed gases and dust, subjected to the same stellar radiation field. While variations exist, with some being richer in carbon monoxide and others in water, depending on their location within the disk and the temperatures they endured, they are fundamentally akin, siblings, or at most, distant cousins. Interstellar comets, however, are strangers. They formed elsewhere under the influence of different stars, within disks possessing distinct compositions, temperatures, and dynamical environments. To date, every one we have observed has been unique. Oumuamua, dry, exhibiting no discernible outgassing, possessing an unusual shape, and mysteriously accelerating. It neither resembled nor behaved like our comets. If it was indeed a comet, it was of a type previously unknown to us. Comet Borisov, also known as 2I Borisov, rich in carbon monoxide. Its behavior was largely consistent with that of a typical comet, yet its gas-to-dust ratio suggested a colder formation environment than most of our comets. It appeared somewhat familiar, yet subtly aberrant, akin to a dialect of a language you already understand. Comet C 2019 Q4, named Three-Eyed Atlas. Gushing water and carbon dioxide at significant distances, containing nickel without iron, and displaying the late appearance of cyanide. None of its observed characteristics align with our prior experiences. It speaks a language we barely recognize. Three distinct objects, each exhibiting wildly divergent chemical compositions. If we extrapolate from these findings, assuming these three represent the broader population, then the sheer diversity of cometary compositions throughout the galaxy is staggering. Not all planetary systems produce comets analogous to ours. In fact, it is probable that most do not. Consider the implications. In some systems, comets might be predominantly composed of nitrogen ice, akin to the surface of Pluto. In others, methane could be the primary volatile substance. In systems with more massive stars, the snow line, the region where water ice can condense, is located at a greater distance. Consequently, comets might form in colder regions and thus carry different volatile mixtures. In systems where giant planets migrate, the protoplanetary disk becomes agitated, mixing materials from various temperature zones and consequently forming comets with unusual hybrid compositions. It is plausible that some comets might contain molecules we have never encountered, molecules that are theoretically possible but necessitate formation pathways absent in our solar system. These could include exotic organic compounds, peculiar ices, or substances that would undoubtedly captivate the attention of any chemist. The universe is vast, and the range of stellar masses, disk compositions, radiation fields, and dynamical environments is immense. Nature thoroughly explores this vast parameter space, and some of the resultant phenomena are bound to be extraordinary. Let us consider this concept further. If life necessitates certain fundamental chemical building blocks, water, organic compounds, phosphorus, nitrogen, and sulfur, then comets lacking these essential ingredients would be sterile, incapable of seeding life or delivering prebiotic chemistry to planets. It is conceivable that many interstellar comets are indeed sterile. Perhaps Oumuamua was merely a lifeless rock drifting through the void. However, if even a small fraction of comets carry the requisite chemistry, that fraction assumes significant importance. This is because comets are cosmic wanderers. They traverse interstellar distances, covering light years. And if they transport organic molecules, amino acids, or even dormant microorganisms shielded within their interiors, then the fundamental building blocks of life can disseminate across the galaxy. This is the hypothesis of panspermia, which posits that life can be transferred between celestial bodies via comets or asteroids. While controversial and currently unproven, it is not an impossibility. And three-eyed Atlas, with its presence of water, organic compounds, and cyanide, contains the necessary ingredients. Not life itself, most likely, but the chemical precursors that could potentially lead to life if delivered to a suitable planet. Each interstellar object we detect expands our sample size. Currently, we have 3. Within a decade, we might have dozens. In 50 years, potentially hundreds. And with each new discovery, we will meticulously measure its composition, trajectory, and activity patterns. We will construct a statistical understanding of the contents of our galaxy. It is possible we will find that water-rich comets are commonplace, that most planetary systems produce them. Conversely, we might discover that our solar system is an anomaly, that water-rich comets are rare, and that most systems yield dry, carbon-dominated bodies. Either outcome is profoundly fascinating, and perhaps, just perhaps, we may one day encounter a comet exhibiting unequivocal biomarkers, molecules that are difficult to explain without biological processes, such as phospholipids, complex organic structures with chirality or isotopic ratios strongly indicative of metabolic activity. Such a discovery would be revolutionary, confirming that life has arisen elsewhere and that biochemistry is not unique to Earth. As of now, we have not made such a finding. Three-eyed Atlas, to the best of our current knowledge, is not carrying life. However, it is carrying information. And information is the fundamental currency of scientific inquiry. Every interstellar visitor represents a gift, a complimentary sample delivered directly to our doorstep. All that is required of us is to examine it with sufficient scrutiny. Part 12. Nickel, a chemical messenger. Let us revisit the anomalous nickel composition, for it is more than a mere curiosity. It is a crucial clue, a chemical fingerprint. And fingerprints, as we know, reveal a subject's origins. Stars function as cosmic foundries. Through nuclear fusion in their cores, they transform hydrogen and helium into heavier elements such as carbon, nitrogen, oxygen, silicon, sulfur, and iron. When massive stars conclude their existence in supernova explosions, the resulting cataclysm forges even heavier elements, including nickel. These elements are then dispersed into space, intermingling with gas clouds, and ultimately becoming incorporated into the formation of new stars and planets. However, the elemental composition varies from star to star. The abundance of heavy elements, a property astronomers refer to as metallicity, is not uniform. Young stars recently formed from gas enriched by numerous supernova events possess high metallicity. Conversely, older stars, which coalesced when the galaxy was younger and fewer supernova explosions had occurred, exhibit lower metallicity. Nickel and iron are both products of supernova, but their relative proportions can differ depending on the type of stellar explosion. Type Ia supernovae, which occur when a white dwarf star accretes matter and explodes, produce distinct nickel-to-iron ratios compared to core collapse supernovae, resulting from the implosion of massive stars. If Three-Eyed Atlas originated from a system whose primordial gas cloud was enriched by an unusual combination of supernova types, its nickel-to-iron ratio could be skewed. Current hypotheses suggest that Three-Eyed Atlas may have originated from the thick disk, an older stellar population. Stars in the thick disk generally have lower overall metallicity, but the ratios of different heavy elements can exhibit variability. If the observed decoupling of nickel in Three-Eyed Atlas reflects the composition of its parent star, then this comet serves as a tracer, providing insights into galactic chemical evolution that are otherwise difficult to obtain. This is because, while we can analyze stellar atmospheres spectroscopically and measure their iron, nickel, and other elemental abundances, stars are located at immense distances. We can only study a small fraction of them in detail. Furthermore, we are unable to study stars that no longer exist, stars that lived and died billions of years ago. However, comets from those ancient systems act as time capsules, preserving the chemical conditions of their birth. If we were able to directly sample Three-Eyed Atlas and analyze its isotopes, trace elements, and mineral structures, we would be holding a fragment of a stellar system that could be billions of years old and thousands of light years away. We would be reading a history inscribed in atoms. Now let us entertain a speculative, albeit fringe, idea that is discussed in certain circles. Could elemental anomalies, such as elevated nickel levels, be indicative of processed material? Not processed naturally, through thermal metamorphism, but rather through technological means. If an advanced civilization were engaged in mining asteroids, refining metals, and constructing structures in space, they would inevitably generate waste products, such as slag, tailings, and exhaust fumes. This material would likely possess unusual elemental ratios due to the selective nature of industrial processes. For instance, iron might be extracted for construction purposes, with nickel-rich residue being discarded, or nickel might be utilized for a specific application, with all other materials being disposed of. If a comet formed within a debris disk containing such industrial waste, it could incorporate these anomalous metals. Subsequently, over millions or billions of years, this comet could be ejected, wander through the galaxy, and eventually arrive in our solar system. We would then detect the nickel anomaly and be perplexed. To be unequivocally clear, there is currently no evidence to suggest that Three-Eyed Atlas is artificial or contaminated by technological signatures. Absolutely none. The concept borders on science fiction. Most scientists dismiss it outright, but it is not physically impossible. And in the absence of a readily apparent natural explanation for the nickel-iron decoupling, even highly speculative ideas warrant consideration. The more probable explanation lies in prosaic chemistry, the presence of nickel within organometallic compounds, fractionation during condensation, or some yet undiscovered process that operates under conditions prevalent in other star systems, but rare or absent in our own. However, it is precisely these possibilities that ignite my scientific curiosity. Every comet carries a chemical signature akin to a barcode encoded in elements and isotopes. By compiling a repository of these signatures and cataloging the compositions of dozens or hundreds of interstellar objects, we can commence mapping the galaxy. We could correlate chemical signatures with their trajectories. A comet originating from the direction of the galactic center might exhibit different elemental abundances than one emanating from the outer halo. A comet from the thick disk could display age-related signatures. We could utilize comets as markers of galactic structure and evolution. Imagine a future where interstellar objects are detected with such frequency, and our detection technologies are so advanced that we catalog dozens of them annually. Each object would undergo spectroscopic analysis. Its trajectory would be traced back as far as possible. Every individual's chemical makeup is logged in the database. Over time, discernible patterns begin to surface. We observe that comets originating from a particular galactic sector are consistently rich in carbon. Conversely, comets from another region exhibit a marked abundance of water. This leads us to investigate the underlying reasons. It's plausible that the carbon-rich zones were the genesis of more low-mass stars, which in turn possess planetary disks with distinct chemical compositions. Perhaps the water-abundant areas experienced more supernova events, thereby infusing the surrounding gas with oxygen. The creation of the 3 Atlas represents the initial phase of this comprehensive catalog. Each entry, each data point, contributes to a growing repository of knowledge. The presence of nickel, with its peculiar, disconnected signature, serves as a constant reminder that every piece of data carries a unique narrative. Each elemental ratio discovered is a vital clue. With persistence and meticulous observation, we can decipher these stories and reconstruct the grand history of our galaxy. Chapter 13, focusing on the unseen population. 3 specific celestial bodies, specifically 2 I Borisov, 3 I Atlas, and 3 confirmed visitors from beyond our solar system, all observed within a 7-year time frame. While this number might seem modest, it's sufficient for statistical analysis, allowing us to estimate the prevalence of other, undetected interstellar objects traversing our cosmic neighborhood. Astronomers have diligently crunched the numbers, considering detection probabilities, the extent of our observational coverage, and the inherent characteristics of these 3 entities. Their estimations suggest that at any given moment, there are likely numerous interstellar objects within the orbital path of Jupiter. These are small, dark, rapidly moving bodies, largely invisible to the majority of our telescopes. Our detection of these 3 is attributed to sheer fortune. They happen to pass in close proximity to Earth, were sufficiently luminous, or appeared in a favorable position in the sky when the appropriate telescope was active. How many have we overlooked? Potentially hundreds or even thousands. For every interstellar comet we manage to identify, it's probable that dozens pass by unnoticed. Some are simply too faint to be seen. Others move at such velocities that follow-up observations become impossible. Still others appear in portions of the sky that fall outside our current monitoring capabilities. Detection is an arduous task, but advancements are steadily making it more feasible. New observational surveys are coming online, boasting unprecedented sensitivity and an expansive view of the celestial sphere. The Vera C. Rubin Observatory, currently under construction in Chile, is poised to meticulously scan the entirety of the visible sky every few nights. This observatory will capture images of everything down to incredibly faint magnitudes, detecting asteroids, comets, supernovae, and any object exhibiting motion or change. Crucially, it will also identify interstellar objects. Current projections indicate that the Rubin Observatory could detect approximately 1 interstellar object per month, and potentially more. This translates to a minimum of 12 such objects annually. Over the course of a decade, this would yield well over 100 confirmed interstellar visitors. This volume of data would constitute a significant statistical sample, sufficient to begin drawing meaningful conclusions regarding their compositions, origins, and overall populations. The Square Kilometre Array, a network of radio telescopes being erected in Australia and South Africa, will also play a vital role. Radio observations possess the capability to detect molecular emissions emanating from comets, even those that are quite faint. The SKA is expected to identify interstellar comets that might elude optical telescopes. Furthermore, space-based ultraviolet and infrared telescopes are anticipated to capture comets that are actively outgassing but are obscured when viewed at optical wavelengths. Each new instrument deployed expands our capacity for detection, enhancing our ability to observe these faint, swift wanderers. However, detecting these objects is only one part of the endeavor. Studying them presents a distinct challenge. Traveling at speeds of tens of kilometers per second relative to the sun. By the time we manage to detect them, analyze their trajectories, and schedule further observations, they are frequently already on their outward journey. The object designated Oumuamua was already departing our inner solar system when it was discovered. We managed a single valuable observation before it receded into the distance, becoming too faint for further study. In contrast, Comet 2I Borisov was observed during its inbound trajectory, affording us several months for detailed examination. Telescopes worldwide were directed towards it, yielding valuable spectral data, light curves, and comprehensive observational records. This represents the ideal scenario. Comet 3I Atlas was also detected relatively early in its approach, allowing for good data acquisition. Nevertheless, it will soon reach its closest point to the Sun, swing around it, and then vanish back into the void. Once it departs, it will be lost to us forever unless we manage to intercept it. Proposals are currently being developed for missions specifically designed to intercept interstellar objects. These spacecraft would be engineered for rapid launch and powerful acceleration, enabling them to rendezvous with an interstellar visitor while it remains within the inner solar system. The technical hurdles involved are immense. Such a mission would necessitate a spacecraft held in constant readiness, prepared for immediate deployment. It would require propulsion systems capable of matching the object's considerable velocity. Furthermore, it would need sophisticated instrumentation for compositional analysis, structural assessment, and potentially even sample collection. However, the potential scientific rewards would be extraordinary. Imagine the possibility of landing on an interstellar comet, drilling into its surface, and collecting ice and rock samples from another star system, which could then be transported back to Earth for in-depth analysis in specialized laboratories. The scientific insights obtainable from such material are virtually boundless. We could determine precise isotopic ratios, offering crucial information about nuclear processes within the parent star. We could analyze complex organic molecules with a level of detail unattainable through remote sensing. It might even be possible to search for amino acids, which are fundamental to prebiotic chemistry, or, with extreme luck, for fossilized microbial life. Even in the absence of finding life, we would gain an exquisitely detailed understanding of the chemical intricacies of alien planetary systems. Every molecule, every mineral, every isotope would serve as a significant clue. Some scientists are already actively engaged in planning such ambitious missions. Conceptual designs are in existence, and budget proposals are being formulated. This is not mere science fiction. It represents a tangible engineering challenge, albeit a demanding one, but ultimately achievable. Within 50 to 100 years, it is conceivable that we will have catalogued hundreds of interstellar objects. We may have successfully intercepted a dozen of them. We might have even retrieved samples from half a dozen. Armed with this wealth of data, we would possess a comprehensive understanding of galactic comet populations, the diversity of planetary systems, and perhaps even the prevalence of the fundamental building blocks of life throughout the galaxy. Comet 3I Atlas offers a preview, a tantalizing glimpse of future possibilities. It demonstrates that interstellar comets are not merely rare oddities, but are, in fact, commonplace, found throughout the galaxy, and are carrying information of immense scientific value. The vast, unseen population is out there, drifting through the darkness, awaiting our discovery, and we will find them. Sequentially, we will catalog them, study them, and meticulously assemble the puzzle pieces that explain planetary system formation, the variations in cosmic chemistry, and possibly the true extent of life's prevalence. Chapter 14. When anomalies converge, time 0.5 seconds. Let us broaden our perspective and examine the larger context, as Comet 3I Atlas is far from the sole perplexing phenomenon currently engaging the attention of astronomers. There are the peculiar odd radio circles, enigmatic rings of radio emission whose origins remain undetermined. Fast radio bursts, millisecond duration pulses of radio energy originating from distant galaxies, with their underlying mechanisms still under debate. Then there is Tabby's star, exhibiting peculiar dimming patterns that have yet to be fully elucidated. And of course, Oumuamua, an interstellar object displaying anomalous acceleration, and 3I Atlas, a comet exhibiting impossible water production and unusual metallic signatures. These are merely the most prominent examples. Dozens, perhaps hundreds, of less publicized anomalies exist. These include transient events that defy existing classifications, spectral features that should not logically occur, and objects exhibiting motion that resists simple explanation. Astronomy is currently inundated with observations that do not conform to our established understanding. This situation is unprecedented. Throughout most of the 20th century, astronomical research was characterized by a scarcity of data. A telescope would be directed at an object, capturing an image or spectrum, and the subsequent analysis would consume months. Discoveries were infrequent, and anomalies were even rarer. When an unusual observation did emerge, it would receive intense scrutiny due to the limited competition for attention. Today, we are overwhelmed with data. Automated surveys generate terabytes of information nightly. Sky surveys meticulously catalog billions of celestial objects. Gravitational wave detectors continuously record cosmic mergers. Radio telescopes maintain a constant vigil of the sky. We are detecting more phenomena than we can possibly follow up on. This sheer volume of data inevitably leads to a higher incidence of anomalies. If one examines a billion objects, even if only one in a million presents an anomaly, that still amounts to 1,000 unusual occurrences. The majority of these will eventually be identified as instrumental artifacts, data glitches, or misclassifications. However, a portion will prove to be genuine, and their thorough investigation requires considerable time. We are currently in an era where anomalies are emerging at a pace that outstrips theoretical development. We are discovering new phenomena faster than we can explain them. This presents both an exciting opportunity and a potential risk. It is exciting because novel phenomena invariably drive advancements in physics. The discoveries of pulsars, gamma-ray bursts, and gravitational waves all originated from unexplained observations. Anomalies are the crucibles of breakthroughs. However, it is also dangerous, as the potential for hype cycles to escalate out of control is significant. Every anomaly is susceptible to being sensationalized as a potentially revolutionary development. Alien megastructures, warp drive signatures, wormholes, or exotic dark matter interactions. The media thrives on such narratives, and the public is captivated. Yet, in approximately 9 out of 10 cases, the anomaly is ultimately explained by something prosaic: dust clouds, instrumental noise, or misidentified known objects. The inherent danger lies in the erosion of credibility. When people are repeatedly exposed to explanations of potentially alien events that are later revealed to be mundane, they may begin to distrust scientists. They might come to believe that science is merely speculative conjecture. Even more concerning, they might double down on the sensational explanation, concluding that scientists are deliberately concealing information. Tabby's star serves as a cautionary tale in this regard. When the hypothesis of an alien megastructure gained widespread media attention, the public embraced it enthusiastically. Social media platforms erupted with discussions, and news articles amplified the speculation. Subsequently, when further observations indicated wavelength-dependent dimming, consistent with dust rather than solid structures, significant backlash ensued. While some individuals accepted the scientific explanation, others insisted that the scientists were either mistaken or deceptive. However, it is important to recognize that Tabby's star remains an object of scientific interest. The dust explanation does not fully account for all observed phenomena. Long-term monitoring reveals complex variability patterns. It is undeniably a peculiar star, possibly surrounded by a debris disk resulting from a planetary collision, or engaged in processes that are not yet entirely understood. It continues to be a subject of legitimate scientific inquiry, valuable in its own right, even if it does not represent extraterrestrial intelligence. The critical lesson here is that anomalies represent opportunities. They compel us to refine our existing models, consider novel mechanisms, and challenge our fundamental assumptions. Even when they do not precipitate revolutionary shifts in physics, they invariably advance our understanding. The anomalous acceleration observed in Oumuamua, even if ultimately attributed to outgassing, compelled astronomers to engage in more rigorous consideration of sublimation at low temperatures, the properties of exotic ices, and surface behaviors. This constitutes genuine progress. Comet 3I Atlas presents another such opportunity. Its observed water production challenges our current understanding of volatile sublimation distances. Its peculiar nickel anomaly forces us to contemplate metal chemistry in comets, a subject we have largely overlooked due to the lack of strong metal emissions in our own comets. Its dominance of carbon dioxide raises questions about the conditions present in protostellar disks in other star systems. When a sufficient number of anomalies are considered collectively, emergent patterns may become apparent. It is possible that odd radio circles and fast radio bursts are interconnected, both potentially involving energetic outflows from galactic nuclei. It's conceivable that interstellar objects like Oumuamua and 3I Atlas represent distinct populations with differing formation mechanisms. Perhaps the transient zoo of astronomical phenomena offers fundamental insights into the energetic nature of the universe. Alternatively, these might all be isolated, unrelated occurrences, individual quirks that happen to coincide within the same few decades due to our enhanced technological capabilities for detection. Either conclusion provides valuable information. The paramount importance lies in maintaining a simultaneous balance of skepticism and wonder. One can be enthusiastic about an anomaly without prematurely declaring it a revolution in physics. It is possible to investigate intriguing possibilities without becoming rigidly attached to them. One can readily revise their conclusions when new evidence emerges. This is precisely where effective science communication becomes crucial. When reporting on 3I Atlas, responsible journalists and scientists should articulate statements such as, "This comet is exhibiting unusual behavior. We are currently investigating several potential explanations. Here is what we have gathered thus far." Avoid sensational headlines like "Alien Comet Defies the Laws of Physics" or "Scientists Baffled by an Impossible Object." Unfortunately, nuance does not typically generate clicks, and careful language rarely achieves viral status. Consequently, the hype machine continues to operate, transforming every anomaly into a potential paradigm shift, thereby setting the stage for disappointment when a mundane explanation is eventually presented. The solution is not to cease reporting on anomalies altogether. Instead, the imperative is to communicate with honesty regarding uncertainty, to present multiple hypotheses, and to provide updates as evidence evolves. The public should be treated as adults capable of comprehending ambiguity, because they indeed are. Most individuals understand that science is an ongoing process, that answers are refined over time, and that admitting "we do not yet know" is a perfectly acceptable response. Comet 3I Atlas represents one anomaly within a confluence of unusual observations. It is significant, it is fascinating, but it is not yet definitive proof of anything. It is a data point, a mystery, and an opportunity for learning. Regardless of whether its ultimate explanation involves a peculiar natural comet or something entirely unprecedented, the very process of studying it, testing hypotheses, and systematically ruling out explanations holds immense value. This process is the essence of science, and science, when conducted with integrity, stands as one of humanity's greatest accomplishments, particularly when grappling with phenomena that remain beyond our current comprehension. Chapter 15. Final Reflections. Alive yet natural. We have now delved deeply into the enigma of Comet 3I Atlas, an interstellar visitor expelling water into space in a manner that defies conventional understanding. It glows with an eerie green hue, attributed to nickel and cyanide, and exhibits intermittent brightening and dimming, giving the impression of deliberate control. It carries chemical signatures from another star system, potentially from an earlier epoch in the galaxy's history. Could it be alive? In a metaphorical sense, perhaps. It is dynamic, undergoing constant change and reacting to its environment. It is active when it should be dormant, and its behavior, though driven by physics and chemistry rather than conscious intent, often appears purposeful. However, in the literal sense of biological life, almost certainly not. There is no evidence of biological processes, no metabolic activity, no reproductive mechanisms, no systems for storing and transferring information. It exhibits none of the hallmarks of life as we currently understand it. Comet 3I Atlas is, in essence, a rocky body coated in ice, warmed by solar radiation, and releasing gas and dust in accordance with fundamental physical laws. Yet, these physical laws are manifesting in ways we have never before witnessed. Water sublimation occurring at distances far greater than anticipated. The presence of nickel independent of iron. A predominance of carbon dioxide. Its intermittent activity suggests a complex internal structure or the presence of unusual ice compositions. Each new observation adds another layer to this intricate puzzle. So, what is it? The most probable explanation is that 3I Atlas is a natural comet that formed under conditions vastly different from those within our own solar system. It might have originated much farther from its parent star, in a colder region where carbon dioxide ice is more abundant than water ice. Its parent star could have possessed an unusual chemical composition, leading to peculiar metallic ratios. It's also possible that billions of years of exposure to space weathering during its interstellar journey have altered its surface chemistry. The organometallic hypothesis is particularly compelling. If nickel became incorporated into volatile compounds, such as nickel carbide, this could account for its decoupled emissions. This scenario would necessitate specific chemical conditions during its formation, which, while unusual, are not impossible. The theory of formation within a thick disk is also persuasive. If 3I Atlas is 7 billion years old and carries isotopic signatures from an earlier era of galactic chemistry, this would explain some of its observed peculiarities. Ancient ice, ancient chemistry, and ancient minerals, all preserved through eons in the frigid depths of interstellar space, are now being revealed as the comet approaches the warmth of the sun. Could it be artificial? Could it be a probe, a derelict spacecraft, or some form of technological artifact? The evidence does not support such a conclusion. Nothing observed about 3I Atlas necessitates a technological explanation. All the phenomena we are witnessing can be, or at least potentially can be, explained by natural processes. Invoking extraterrestrial intelligence is unnecessary. However, let us entertain this notion for a moment. If one were to design an object intended to survive an interstellar journey and remain detectable billions of years later, how might they proceed? A comet-like object would likely serve as an effective shell, its payload protected by layers of ice and rock. Unusual chemical signatures might be incorporated as markers designed to stand out to anyone analyzing its spectrum. Natural sublimation as the object approached a star would then reveal these markers. This is purely speculative. There is no direct evidence to support it. However, it is worth considering that if we ever encounter an artificial interstellar object, it might not initially appear artificial. It might resemble a comet, an unusual one certainly, but one whose peculiarities could be explained by natural phenomena until a deeper examination is conducted. Is 3I Atlas such an object? Probably, almost certainly not. But the very fact that we are posing the question speaks volumes. It indicates that this comet is sufficiently strange to stretch our imaginations, prompting us to contemplate possibilities we would otherwise readily dismiss. And perhaps herein lies its true value. Not whether 3I Atlas is natural or artificial, nor whether its chemistry is merely unusual or genuinely groundbreaking, but that it stimulates our thinking. It compels us to question our preconceptions. It serves as a potent reminder that the universe is far larger and more enigmatic than our immediate cosmic neighborhood, and that nature, over billions of years and across trillions of star systems, has had ample opportunity to explore the vast spectrum of chemical possibilities. We, in our limited scope, have barely begun to survey what is achievable. Every interstellar visitor presents a challenge. It challenges our models, our theories, and our established notions of what constitutes normal. And it is through challenges that we achieve growth. Oumuamua challenged our understanding of cometary activity. Comet 2I Borisov prompted us to reevaluate our assumptions regarding carbon monoxide abundances. Comet 3I Atlas, however, is challenging our understanding on multiple fronts. Volatile budgets, metal chemistry, activity distances, and compositional diversity. The next steps are clear. We must continue to observe 3I Atlas as it approaches perihelion, meticulously measuring every possible parameter: spectra, light curves, gas production rates, and dust-to-gas ratios. We need to search for new emission lines. We must observe whether iron finally becomes detectable or if the nickel anomaly persists. These observations must be compared against existing models, leading to refinements and the generation of new predictions, which will then be tested. Furthermore, we must prepare for the inevitable arrival of the next interstellar visitor, and the one after that. The galaxy is teeming with these cosmic wanderers, and our detection technologies are improving year by year. Each new arrival will present a fresh puzzle, a new set of clues, and an invaluable window into the processes of planetary system formation and evolution across the diverse range of stellar environments. Perhaps one day we will succeed in intercepting one of these objects. We will land on it, drill into its surface, and bring back samples. We will analyze its isotopes in terrestrial laboratories, examine its minerals under electron microscopes, and search its organic inventory for prebiotic molecules, thereby acquiring knowledge that we cannot even conceive of at this present moment. Until then, we will watch, we will measure, and we will wonder, for this is fundamentally human nature. We gaze at the universe and pose questions. Why is that comet active so far from the sun? From whence did it originate? What can it teach us? These questions themselves hold inherent value, even preceding the discovery of answers, for it is questions that initiate exploration. Comet 3I Atlas journeyed from some distant location, traversing light years and billions of years, carrying a message encoded in water, nickel, and cyanide. We did not solicit this message. We do not yet fully comprehend its content, but we are actively listening, observing, and learning. And in this act of learning, in this persistent dedication to understanding, we discover something that might be the closest approximation of life within this entire narrative. Not the comet itself, but us. Curious, wondering, reaching out to touch something that originated from an unfathomably distant place, striving to decipher a communication from another world. The universe continues to dispatch these missives, cosmic postcards, messages in bottles, visitors emerging from the darkness. And with each arrival, we are reminded that we inhabit a vast, ancient, and incomprehensibly rich cosmos. A cosmos that will perpetually exceed our understanding, forever surprise us, and eternally present new mysteries. Comet 3I Atlas is one such mystery, one comet among an infinite sky. However, it is now our mystery, and whether it proves to be merely a chunk of ancient ice or something more, whether its secrets yield readily or prove elusive for decades, we will persist in our observation. We will continue to ask questions. We will remain attentive, endeavoring to discern what the universe is attempting to communicate. For this is the essence of being human, to perceive something anomalous in the night sky and to refuse to avert our gaze, to demand answers, even when the universe remains silent, to find wonder in a transient expulsion of water molecules, occurring at a rate of 40 kilograms per second, in the ethereal green glow of nickel that should not be present, and in a trajectory that points back towards stars we will never reach. We are infinitesimal. The universe is immeasurable. Yet, a dialogue unfolds between us and that immense expanse, bridging our observational instruments and those far-off celestial wanderers, connecting our inquiries to any resolutions we may uncover. This is a protracted exchange, a gradual discourse unfolding across generations and across the vastness of space, encoded within the very particles of light, the signatures within spectral analyses, and the predictable paths of celestial bodies. The third atlas uttered its pronouncements. We registered its message and remained attentive, anticipating its subsequent revelations.